So in the previous chapter, we talked about all the properties of the connectivities of graphs, right? In particular, there were nice tools on three connected graphs, which allows us to apply inductions. So now we're gonna turn our attention to planar graphs. So let's begin with the definition. So what is a planar graph, right? And before that, I want to say the distinctions between planar graphs and plane graphs. So let me start with the definition of plane graphs. A plane graph is really a graph on the plane such that V is this just a subset of R square, so which means that V is a set of points on the plane. And what about E's? Every edge is an arc joining two vertices. Okay, its end, right? And this is the most important condition: the interior of an edge contains no vertex. And no internal, no point. I don't have to say, so no point of any other edge. Okay, so for example, so this is not a plane graph. Why? Because this edge contains some point here, right? And this is not the only example. So for instance, I cannot have an edge like this. So this is not a plane graph. Or I cannot have an edge like, if I have an edge like this, that's forbidden. What are the plane graphs? So, oops. This is a plane graph, right? So in the definition of plane graph, you don't allow two edges to cross, and you don't allow an edge going through the other point, representing a vertex. And then we say that a graph is a planar. If it is isomorphic to a plane graph, then we say the graph is planar. So this graph is planar. Why? Because this drawing itself is not planar. This drawing itself is not a plane drawing. I should maybe define drawing and embedding. Okay, but it is isomorphic to a plane graph shown here, right? So this is a plane graph. All right, so let me define a drawing. So what is a drawing? just to have a vocabulary. Drawing of a graph on a surface S is a mapping from a graph to S so that vertices are mapped to distinct points in S, and edges are mapped to an arcs joining 2 points corresponding to its ends. And it is possible that you might have a loop. In that case, edges are mapped to a loop. An edge is mapped. So, for instance, if I have a loop, then this could be a drawing. And we say that two edges okay, am I doing all right? So two arcs cross if they have an intersection point that is not an end point of both arcs. So we say, like, if you have two arcs, it looks like this, then we say that these two arcs cross. This is a cross, and this is not a cross. Maybe I add extra conditions. So the edges are mapped to arcs joining 2 points corresponding to its end, and there being no point not corresponding okay, let me each edge is mapped to an arc joining 2 points corresponding to its end and having no point corresponding to not corresponding to its end. So I'm requesting it to, not going through any other points representing a vertex. Okay, so maybe a better way of writing it, no point corresponding to a vertex other than its ends. Okay, so this is better, right? All right. Yeah. So then, what's an embedding? an embedding of a graph on a surface S is a drawing of a graph G on S such that no two edges cross. All right. Now, and then we say that a graph is embeddable on a surface S if it has an embedding on S. Okay. So now another way of saying that, way of saying a plane graph is an embedding of graph on a plane, in a sense, right? And a graph is planar if it has a planar embedding. Right, so planar embedding. What is that? Like embedding on the plane. Anyway, now sometimes plane is not a good surface to study because plane is not compact, and many people would prefer to study some compact surface. So instead of plane, right? So it's huge. How about surface? Sphere. Oops. Yeah, I'm not really good at drawing sphere. And here's the first observation that many of you may have seen it in the discrete math course. A graph is embeddable on a plane if and only if a graph G is embeddable on a plane if and only if it is embeddable on the sphere. Does it make sense? So why is this true? So one direction is true. Imagine that you draw the graph on the plane and you shrink the picture as far as you can. So shrink it. So now you have a piece of paper and you're living on Earth, you put it on somewhere. And that doesn't create any crossings, right? So if I do have embedding on the plane, then I shrink a lot, and then on the Earth you put it somewhere, and that's still an embedding. So that direction is clear in a sense, but actually there's a better way, and the second picture will show you that this is not the only way to find an embedding of a plane graph on the sphere. All right, so if I have a graph embedded on the sphere, how do I get a planar embedding? That's when we're gonna use stereographic projections right, so maybe all right, think of the equator of Earth. Okay, now I have a plane cutting through the equator of the Earth, okay, in the middle. Now I have one light bulb on the North Pole on the sphere, and when I choose the North Pole, I'm going to choose the place which is not on any arc or vertex. All right, so whenever I choose North Pole, I always choose a place outside of my embedding. And this can be done always because, why? Because arc is closed set, right? Arc is closed. I mean, what's the best way of, yeah, so it's a continuous there's a continuous function that maps this Z1 interval to an arc, right? So the image of this closed interval must be a closed set, and this sphere is compact set, so it's a closed subset of compact sets, so it's going to be compact. I mean, there are better ways. There must be better ways to explain it. So the union of all the arcs and points on the graph is a closed set, right? So the complement is open. So I can find the place, like this point, North Pole, so that around its neighborhood, there is no point used for arcs and vertices. Right, so that's where I choose the North Pole. All right, so whenever I have a point other than North Pole, I can draw this straight line going through these North Pole and these red points, and that will have a shadow on the plane. Okay, so any points on the sphere will give me a point, even at the bottom. Oops. Right? So this is called the stereographic projection. So that gives you a one-to-one correspondence between the sphere minus North Pole and R2, right? Except the North Pole, every other points will have a unique points associated, and this function is continuous. So any continuous curve will be mapped to a continuous curve. And if you have taken a course on, I guess it's probably topology, or yeah, you must have seen it. All right, so whenever I have a drawing, the embedding on the sphere, I can find the shadow on the plane. All right, so and no two edges will cross, it's just a shadow. So therefore the graph is embeddable on the plane if and only if it is embeddable on the sphere. All right, there are other terminologies. What about, okay, so let's define a face. A face or region is a connected component of R squared minus the image of a graph. Okay, let me be more precise. Face of a plane graph G R squared minus all points on G. So when I say all points, meaning vertices and arcs. So what does that mean? That means if I have a plane graph like this, right? And then what are the faces? So this is one face, right? So 2 points are on the same face if there is a curve connecting them without going out, on staying inside, right? So after deleting all these black lines, then you distinguish points on the plane by saying, oh, these 2 points are connected by a curve on this set. Then we say that these two are in the same component. So then the plane minus all the edges and points will split the set into connected components. Yeah, so this is another connected components, and that's another one, and that's another one. Is that all? No, there's one more, right? There's one more here. So in this picture we have 1, 2, 3, 4, 5. So 5 faces. Okay. Now you see that the boundary of the face could be very complicated, right? Moreover, 2 graphs could be isomorphic, and yet the boundary may look right. In terms of graph theory, these 2 graphs is isomorphic. So let me draw this picture. So these 2 graphs are isomorphic as a graph, but as an embedding, they are somewhat different. How do I know that they are different? I will focus on right. So if I look at this face, so previously in the previous picture I have a face boundary that consists of this many edges, so 7 edges. This contains 1, 2, 3, 4, 5, 6, 7, 8 edges, right? So if these 2 embeddings were identical, the equivalent one, topologically, or if we can convert this embedding to that embedding, then this embedding must have a face incident with the 8 edges, but there's no such face. So they don't have a equivalent embedding. In some sense, right? Sometimes you might have embeddings that look different, but in fact they are equivalent. So what are the examples? So how about these 2? You may say, oh, these 2 looks different, but actually when you draw them on a sphere, if you draw them on a sphere, here's a North Pole, and if North Pole is here, then what you get is this picture. But if your North Pole is here, then what you get is this picture. Alright? Because this point will be closer than that line, right? So these 2 are essentially the same embedding on the sphere. It just matters, what's different is the location of the North Pole, where you do the stereographic projections. Right? So in that case, these two are essentially the same embedding. So these two are different embedding. These two are different embedding. These two are same embeddings of the same. It's same embedding on the sphere. All right. So this, in the beginning of the course, I remember saying that graph theory is the study of graphs, study of properties of graphs invariant undertaking isomorphisms. So in some sense, this is not invariant on the isomorphism, right? So this is not invariant, right? If I have a plane graph like this, I have a face instead with this thing, I don't have a face. So faces are in a sense not really, I cannot say that my graph has a, so what I want to say is, if I state the theorem for planar graph, then embedding might not be unique, right? There are two different embeddings, so I cannot say certain things, right? So for instance, do I have a face of size something? This property is not determined by the planar graph, because you might have many different embeddings. All right. Now I will tell you a theorem about two connected planographs, which will clean up a little bit of dirty things on planographs. So here's the theorem. Let G be a two connected loopless plane graph. Then each face boundary is a cycle, and every edge of G is in exactly two faces. Okay, I should say instant with exactly two faces. Without this condition, I know that an edge is instant with one or two faces, because if I have an edge, then all these points on the right hand side are on the same face, because I can connect them. All these points on the left hand side are on the same face because I can connect them. There is no other edges crossing this line, right? No other edges preventing it. And the question is whether or not these two faces are one. And it's possible that these two faces are actually the same face. So for instance, in this example on the left hand side, this edge is instant with only one edge, one face, right? These two are on the same face. This edge is instant with the two faces, right? This edge is instant with the one face. And this theorem tells you that such a dirty case never happens when graph is two connected. So how do we prove that? We use induction on number of edges. Okay, if G is a cycle, if graph is a cycle, then you're splitting the plane into two regions, inside and outside. So these two faces are distinct and they're not equal, and every edge is instant with these both faces, so then it's trivial. If G is not a cycle, then by the ear decomposition, every two connected graph is built from some cycle of length at least 3 by adding ears and loops. And since this graph has no loops, it can be built from cycle by adding ears and ears and ears. So remember, think of the last place, like each intermediate step gives you two connected graphs. So there is a two connected subgraph H such that G is obtained from H by adding an ear P. So this is some big graph H, and we are adding some ear P. Now we apply induction hypothesis. Right, H is a subgraph, so H is a plane graph again. By the induction hypothesis, each face of H is bounded by a cycle of H, and each edge of H is incident with exactly two faces. Now, so that means there is a face containing all the points on this blue edge, it's blue path, right? So there used to be a face containing this, and this face was bounded by a cycle, and path was going through it. Now, all other faces stay as faces bounded by a cycle. Okay. So now what happens with G? In G, every face other than this particular face, it stays as a face, right? So what should it be? Yeah, so P is contained entirely in one face, let's say C of G, no, C of H, and then P splits C into two faces, C1 and C2 of G, right? Because if I split here, this is P, I used to have this single face. Now the question is, after adding this path, can these two faces to be same face? If they are same face, then I must have a curve connecting these two dots. Is this possible? No, because it's bounded by this cycle, right? So there's no way of escaping from here to there. So I'm cheating a little bit because this is not a trivial fact. I will tell you what it is later, but this is not a trivial fact. Has been it took many years for mathematicians to come up with the correct proof, but we will take it for granted. Okay. Now this P splits C into two faces, so every edge on P is incident with both C1 and C2 and not incident with any face. And how about others? So by the induction hypothesis. Okay, so what should I say? Did I say already? By induction hypothesis, every face of H is bounded by a cycle. So except C, all other faces are already bounded by a cycle of G. So that's it. So that's the first case. And then for every edge, they were incident with the two faces, and adding an edge doesn't change that, right? You add one more path here, and you will never merge two distinct faces into one face. So this proves the so that's it. Maybe I should say it is easy to observe that every edge of G not on P is incident with two faces of G because it was incident with two faces of H, right? So what used to be, these two used to be distinct, so adding an ERP doesn't merge them. Okay. Now I said that I cheated a little bit because I was assuming Jordan curve theorem twice in this proof. So where did I assume this? So this is one part, and that's another part. So I have two places that I use Jordan curve theorem. So this is so if you take the course on differential geometry, you will learn this course, this theorem. There's also a combinatorial proof of that, assuming a slightly simpler version. Instead of allowing all possible arcs, you may do all the graph theory on the plane graphs by using piecewise linear straight line segments. Instead of allowing every curve, you may allow like finitely many collection of straight line segments and do the same graph theory again, and nothing changes. So you can prove a Jordan curve theorem in this version, and then you can prove it combinatorially. But anyway, let me tell you what the Jordan curve theorem is about. So any simple closed curve on the plane okay, deleting any simple closed curve on the plane results a partition of the what will be result two components. sharing, okay, let me say this is C, sharing C as their common boundary. So if you delete the points, if you use scissors to cut the plane by following simple closed curve, then you will have two faces, face 1 here, face 2 here. A simpler version, more complimentary proof, can be proven if you assume that C is a polygon, right? Oops. Let me try it again. So why is this non-trivial? Because, oops. Okay. Let me try again. This could be your curve, right? And then Jordan curve theorem says that when you cut this out from the plane cuts, then you have two pieces. Now this is not a trivial thing, and Jordan's initial proof was not correct, and the actual correct proof was done by some other mathematician many years later. There's even a paper proving Jordan curve theorem formally by using computer software, because people want to have a precise proof, and Jordan curve theorem is one of the classical examples where many people made wrong proofs. Anyway, I'm not gonna describe the proof. For general version, this simpler version, when you use instead of a closed curve, if you use a polygon, then there is a proof based on some idea like this. You move this curve like x-axis vertically, and then track what happens. And there's an observation that if you have a line going through here, then this must be outside, this must be inside, this must be outside, inside, outside, inside. So that kind of thing. So you use this kind of observation to do induction. So you move this line parallel, which is not parallel to any line segments, and then see what happens. So that kind of proof is known. But anyway, we're not gonna show the proof. All right, so we've been using Jordan curve theorem already twice to make sure that this easy case is actually a true statement. All right, so if we use Jordan curve theorem, you can prove that some of the graphs are not planar. This, like K5 is not planar. No matter how you try to draw K5 on the plane, you're not gonna have a planar embedding. Why? Let's start with K1. K1 is planar. What about K2? This is unique drawing. K3, this is essentially the only drawing, only embedding. What about K4? Now, from K4, if I delete one vertex, then it's K3. Then I said that this is the only drawing of K3. So I already have a K3. So it's enough to add one more vertex. And if you think of the stereographic projections or embedding on the sphere, then inside and outside have symmetries. It doesn't matter where to put the last vertex, inside or outside, because I can always invert it. You draw the same graph on the sphere and rotate the sphere so the north pole is where you want, and then project it again then you can change inside and outside in this space. So I can draw the last vertex here. So that's the only drawing, the only embedding of K4 up to this rotational symmetry. How about K5? So I already know that K4 has this embedding. This is the only embedding of K4. And if I try to add one more point, but again, all the faces are symmetric. If you you may say that this region outside the region looks different than others, but again, if you draw on the plane on the sphere, then all four regions are actually identical. You can rotate the sphere and project it again. You can make any face you like to be an infinite face. Did I define these words? Or infinite region, sometimes called the unbounded face or outer face. All these words are same. All right. So there's no difference of the particular infinite face because on the sphere everything is identical. Now let's look at let's try to draw the last vertex somewhere, and then I can add the three edges, but I cannot connect these two. Why? Because there is a simple closed curve here which separates the plane into two pieces, inside and outside, and one of them is already inside and this is outside. There's no way to connect them without crossing the red line. So that's why K5 is not planar. And similarly, we can talk about K33. So let's start with the K22. So this is K22. You have two vertices. It's planar. How about K23? If I delete one vertex from K22, I have a square, and inside and outside there's a symmetry, so I can assume that the last vertex is inside, and then I can draw them like this. So this is the only embedding of K23 on the plane up to this rotational symmetry of the sphere. How about K33? Now, if I delete one vertex, I have this graph. Now again, these three faces are symmetric. If you draw on the sphere and rotate the sphere, put somewhere on if you move some North Pole over here and project it again, this face will become the infinite face. Okay, so there's a symmetry. And if I put the last vertex over here, then again there's a red cycle, and this is inside, this is outside. There's no way to connect these two without crossing red cycle, so this is not planar. So we see, so this says that not every graph is planar. Okay. Now what else? Yeah, so we talked about two connected graphs. So why is two connected graph nice? Because if it's planar, then it has embedding such that every face is bounded by a cycle, and every edge is instant with exactly two faces. But still, two connected graphs do not have a unique embedding. We have seen this example. Oh no, we haven't seen the example. Do we have an example? Okay, let me try to draw some example where you don't have a unique embedding. Yes, so let's see whether I can make it. All right, uh, let's try. These are two connected graphs, isomorphic to each other, and now are they same embedding on the sphere? No, why not? Well, let's look at the faces. So this face is instant with the 3 edges. This face is 1, 2, 3, 4, 5. 5 edges. 3. This is sometimes called the face degree. 3, 4, 3, 4. And then outside is like 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Right? So this face degrees are different. So there's no way that these two embeddings are same. And this graph is two connected. Now, what we're gonna say is that if planar graph is 3 connected, then there's only one embedding on the plane. Unique embedding is a really nice property to have, because when you prove that this K5 is not planar, we use the fact that K4 has unique embedding, right? And this kind of property is very useful when you study the embeddability of graph on the plane, because if you don't have a unique embedding, then it's difficult to say whether some graph is not embeddable, because you delete one vertex and see what happens, or you delete one edge and see what happens. And if you had a minimal case, you have a situation where you might have many different embeddings, and then you try to extend by adding one edge, and you have to say that none of them works. If you have unique embedding, you don't have to do that. And later we will see the Grotowski's theorem, and in the proof we use this property that some graphs have a unique embedding. So what graphs have unique embedding? There is the planar graphs, the 3 connected planar graphs. So let G be a simple, okay, I also need the simple 3 connected plane graph. Then we already know that every face boundary is a cycle of G, but C is a face boundary if and only if C is a non-separating induced cycle of G. So I didn't say what non-separating means. So C is non-separating if G delete V of C is connected. C is induced if C is an induced subgraph of G. So which means that two vertices are adjacent, two vertices of C are adjacent in G if and only if they are adjacent in C. So this is induced cycle. And this is not. If I had an edge is not an induced cycle. Okay. What about separating? So this is separating cycle. And it's non-separating. Well, for instance, this something like this. So why is this statement interesting? Because on the one side, we're talking about the geometric property. Something is a base boundary. It depends, totally depends on the embedding. And the other side is nothing to do with geometry. A cycle is non-separating. Well, you can decide by deleting it and see what happens. And we can decide whether cycle is induced. So that means on the right hand side here, everything is determined by the property of graphs, combinatorial property. So this geometric property is determined by combinatorial property as long as you have this connectivity requirement. And there's a stronger theorem saying that not only the list of phase boundaries are same, but the embedding is identical, but I'm not going to prove that. That's a Wittin's theorem, but we will see this weaker theorem. So as long as two planar graphs are as long as a planar graph is three connected, all embeddings have the same list of phase boundaries. So you don't have things like this. Okay. So why is this true? All right, so should we try to prove this? Suppose C is a phase boundary, and I want to prove that it's non-separating. If C is a separating, then there are vertex. The two. If C is separating, then there is a pair xy of vertices of G delivery C such that G delivery C has no path from x to y because it's separating. Now, by Menger's theorem, G has three internally disjoint paths. Let's say P1, P2, and P3 from x to y. So I had three paths, P1, P2, P3. Now, the cycle C cannot be. I mean, these three paths partition the plane into three pieces, right? 1, 2, and 3. So P1, the R2 minus P1 union P2 union P3 partitions the plane into three regions, right? C belongs to one of them, And by symmetry, yeah, I don't have to write. By symmetry, I can assume that C is here. Assume C is in the region bounded by P2 and P3. But then this P1 is a path joining X to Y without hitting C. Right? That's contradiction to the assumption that that is non-separating. Oh, contradiction to the assumption that it is a separating. So, contradiction. C is non-separating. Okay? Now we proved that C is non-separating. How about induced? So suppose C is not an induced cycle. So you have C and you have an edge like this. Now, if it's not an induced cycle and graph is simple, so you don't have a parallel edges. So I must have a vertex here and vertex there. C has two vertices, X, Y, on its subpath joining two ends of a chord. Right. So, now this is a chord. I have two subpaths, and in both sides you can choose X and Y. Right. And now graph is 3 connected, but how is it possible? Oh, by the way, if I draw C over here, the outside is, if I draw cycle C, either inside is completely empty because it's a face, or outside is completely empty. But let me assume that outside is completely empty by symmetry because I can draw the graph on the plane. And then outside is empty, and I can delete these two vertices, and then there is no path from X to Y. So there's no path from X to Y exists if we delete two ends of the chords. That's contradiction. Okay? So that proves the graph, this cycle C is induced. How about the converse? Right, suppose I have a non-separating induced cycle. Is it a phase boundary? Okay. If C is a non-separating induced cycle, and this direction is easy, then by Jordan curve theorem, C splits the plane into two regions, right? So you have a C, and inside and outside will be different. Since C is non-separating. One of these two has no vertices, right? And since C is induced, there's no chord drawing. So this means that these are phase boundary. Okay. So that's it. So here's a very nice corollary of that. If G has 3 non-separating induced cycles sharing containing E, so let E be an edge. If graph has 3 non-separating induced cycles containing E, then G is non-planar. Why? Because any edge, okay, maybe I should say graph is 3 connected. G be a simple 3 connected graph. Because if graph is planar, then every edge is instant with exactly 2 faces. Because it's 2 connected. 3 connected graphs are 2 connected. Every edge is instant with exactly 2. But here you say that you have 3 non-separating induced cycles. So if it's planar, then all these 3 cycles should be a phase boundary, which is impossible. You only have 2 faces. So it's trivial. Now, why is this interesting? Let's look at the K5. K5 is 3 connected. Simple. You pick any edge, then how many non-separating induced cycles do I have? 1, 2, and 3. The 3 non-separating induced cycles containing particular edge, so K5 is non-planar. How about K3? This is again 3 connected simple graph. Right? Now I pick this edge E. So 1, 2, and 3. Right? There are 3 non-separating induced cycles. Again, actually there are more. There are more, 4. But this is already enough to prove that these graphs are non-planar. Right. Okay. Oops. All right, so that's it for this lecture. So in the next lecture, we're going to prove the Euler's formula and Grotowski's theorem. Okay, bye-bye.